Yeah, hi, welcome, and thanks a lot to the organizers for giving me the opportunity to talk here. And I want to talk about some unexpected Trotter error scaling, as announced already, for realistic quantum system. And by this, I actually mean quantum systems which have continuous degrees of freedom. And I don't want to truncate them, so I want to study the full unbounded system. And I want to look at quantum chemistry problems here. And this is joint work with Daniel, Paulo, Matthias, and Kazuya, and you can find it on the archive. First of all, this is some small outline of what to expect in this talk. So I first want to talk a little bit about the motivation behind this project and what's the state of the art of bounding Trotter error and Trotterization in general. And then afterwards, I want to look at the hydrogen atom in particular as a very paradigmatic example that captures a lot of analytical insights of quantum chemistry problems. And at the end, I also want to talk a little bit about higher order Trotter product formulas and what we can learn in that case. So I just briefly, why do we even care about Trotterization? So Trotterization, or the Trotter product formula, appears in a lot of areas in quantum physics. I don't want to mention all of these. I just want to focus on this part of Hamiltonian simulation and quantum chemistry because it kind of neatly blends into this session here. But roughly, the idea of Trotterization is you have some target dynamics that's given by some operator h1 plus h2, and that's very difficult to implement. But you can implement the dynamics under h1 very easily, and you can implement the dynamics under h2 very easily. And so you want to basically split the dynamics under h1 plus h2 into its individual components, and you use the Trotter product formula to do so. Example of this would be like Schrödinger operators, where you have potential energy plus kinetic energy. And so the way it works is basically you have some total time evolution t, you evolve for some time t, and you split this time into smaller intervals, and you just alternate very quickly between h1 and h2. And so this is how it looks like in formulas. If you do this approach, you actually make a small error because h1 and h2 do not commute with each other. And so the question is, what is this error, and can we make this error as small as possible? So the way currently people think about Trotter errors, and this is this very influential paper by Andrew Childs and collaborators, is with this bound here, which has this 1/n scaling and also a commutator bound. So this is nice because you want to take into account that if the Hamiltonians approximately commute, then the Trotter error becomes smaller. And so this is bounded in the operator norm. So in the case of matrices, this would just give you the largest singular value of this matrix. And so this is kind of intuitive, this bound, because you can basically think of Taylor expanding the target evolution, and you could also Taylor expand the Trotter evolution. And if you just subtract the two Taylor expansion, you get something that gives you exactly this scaling. I don't know what's wrong with this. But yeah, okay, that's the commutator. And you get some 1/n scaling in the number of Trotter steps. So this is all kind of very intuitive and kind of nice. So the question is, what else can we do here? And so we can basically look at some systems, like some practical systems, like the hydrogen atom, and we could think of Trotterizing between kinetic energy and potential energy. And so these are two unbounded operators. They live on an infinite dimensional Hilbert space. And if you compute their commutator and you compute the operator norm of that commutator, you'll find that this is infinity. So this bound is kind of useless because it tells you that the Trotter error is smaller than infinity, which, yeah, is not very helpful. So actually what we have to do is we have to incorporate the dependency on the actual input state, because the operator norm is the supremum over all input states, so it gives you the worst case scenario. But usually in a physical situation, we want to look at some particular input state, and for this we can actually hope to get non-trivial Trotter bounds. And in the case of quantum chemistry, we are usually interested in spectral information. That's why we want to look at eigenstates of the target Hamiltonian. So we basically have to look at this quantity. So we want to look at the Trotter evolution applied to an input state minus the target evolution applied to some input state in the normal L2 norm of the Hilbert space. And so this is our first contribution. So we actually found bounds that give you, that actually compute exactly this. And so these bounds have a quadratic dependency, so I act with h1 squared on phi and with h2 squared on phi, and this h is just the eigenvalue of this phi. And so with these bounds, we can for the first time compute the Trotter error bounds, non-trivial Trotter error bounds for continuous degree systems, so for atomic and molecular Hamiltonians. And for example, if I look at the hydrogen atom, I can look at the well-known eigenfunctions where I label them by the principal quantum number, and L and M give you the orbital angular momentum. That's like undergraduate physics, I guess. And so we get this really nice bound if we look, for instance, at the 3 to 0 state, and we get the expected 1 over n scaling that we also got from the finite dimensional bounds. And you can also convince yourself numerically that that you get the scaling and everything is kind of nice. But usually you are interested in quantum chemistry in things like what are ground state properties. So maybe we want to look at the ground state. And so I already told you that the bounds that we found depend on h1 squared applied to the state and h2 squared applied to the state. But it turns out that the ground state is not in the domain of h1 squared nor of h2 squared. So you can't even act with these operators on the ground state. And so our bounds also trivialize. And so in this case, we have to do some more refined analysis, and we were actually able to do that, and we find some, more complicated looking bounds, and we can analytically compute all these quantities for the hydrogen ground state. The bounds look a bit scary, but basically what I want to tell you is they scale slower than 1 over n. They scale as 1 over n to the 1/4. And this is rather surprising, I think. And in fact, we find that this scaling holds for all s orbitals. So the scaling completely depends on the orbital angular momentum quantum number. And also for p orbitals, we find a slower scaling. And for higher orbitals, the scaling that we know from the finite dimensional systems holds true. Well, and now this is all just upper bounds. So we want to know, are these actually, do we actually get the scaling, or is it just some artifact? And so we looked at this problem numerically as well. And we find that numerically, we also get a slower scaling that coincides with the scaling that we find analytically. And the way you actually see this is you look at the hydrogen atom and you truncate it. So you make it finite dimensional to put it on your computer and do the simulation. And you look at the Trotter error on higher and higher truncation dimensions. And what you see is that for some large number of Trotter steps, you get this 1 over n scaling that you expect. But for some small number of Trotter steps, you get a slower scaling, and then there's a transition region. But this transition happens later and later to the higher and higher truncation dimensions you go. So ultimately, in the limit of infinitely many dimensions, so in the full system limit, where you study the full continuous model that you're actually interested in, the full hydrogen atom, the scaling just stays slower, and this transition to the 1 over n scaling will never happen. And so the way you can think about it physically is in the following way. So the s orbitals, including the ground state, they have a high electron density close to the nucleus, which is where the 1 over r singularity of the Coulomb potential sits. And so in the Trotter evolution, we evolve under the bare potential energy. And so this means something bad happens, because this state is very singular in the potential energy. And so what actually happens by the Trotter dynamics is we get some ionization. And we can see this numerically as well. We find that the s orbitals ionize much more heavily than, for instance, the d orbitals, for which we really get the scaling as in the finite dimensional case, the 1 over n scaling. So this is some physical way to think about this. So you might want to ask, how applicable is this result? Because for now, this is just, we study Trotter of potential and kinetic energy, and often people do some second quantization approach, do some Jordan-Wigner transformation, and this is kind of different. But I want to point out that I would expect that something similar would happen in this scenario as well. It's a bit more complicated to study because of this pick and mix procedure where you, in your Jordan-Wigner transformation, check which terms are commuting and which ones aren't. But also, there are a lot of papers which really do it in the same way as we do it, where it's trotterized between kinetic and potential energy. And this is kind of an appealing approach, because the potential energy is already a diagonal operator, and the kinetic energy is easy to diagonalize. You essentially do a Fourier transform. So you can implement the dynamics under each individual term very easily. And that's why this is a appealing approach to tackle trotterization. The second thing I want to mention is, there are other methods to do Hamiltonian simulation as well, like qubitization, linear combinations of unitaries. And I would honestly expect that some similar effect from the unbounded nature of these continuous degree Hamiltonians would appear in these studies as well. It's just not been studied yet. So I think this is some very interesting problem to study. And in fact, in this paper here, there has been a qubitization approach that also concerns a continuous degree Hamiltonian, and that's been compared with the Trotter approach. And also in the limit of infinitely many truncation dimensions, their bounds in the qubitization case diverge. So this gives some indication that there is something here as well. So some extra care has to be taken if we want to look at these continuous degree Hamiltonians. Okay, so the next question you might want to ask is, if I'm doing the simulation on my quantum computer or even on a classical computer, I will always truncate my model. And so what's the role of the truncation? Like I will always only work with a finite dimensional model. So why do I even care about this full infinite dimensional limit in the first place? Well, the answer to this question is because in this case, the truncation itself becomes the dominant source of error if you have this slower scaling. And this is a little bit discussed in this paper here. From this paper, I also took this graphic here where you basically look at the trotterization between the harmonic oscillator and the generator of the squeezing transformation. And you take the number of Trotter steps constant, and you just increase the number of truncation dimensions. And you'll see that you pretty fast reach the number 2 for the Trotter error, which is the maximum you can actually get for the Trotter error. So there's a very intricate interplay between Trotter error and truncation error. And if you increase the truncation dimension, you would also have to increase the number of Trotter steps in order to get accurate simulation. So basically, it would be important to study this kind of connection between Trotter error and truncation error in more detail. But yeah, our results hold for the full unbounded case. So they apply without truncation even. Okay, so I also promised you that I will talk a little bit about higher order trotterization, because this is what many people do. First order trotter is, converging slower, and there are kind of like second order trotterization where it converges as 1 over n squared. Like you can also change the order of the Hamiltonians here. You can do fourth order trotter, which converges as 1 over n to the 4. And you can go to higher orders, and in general you can find formulas which converge as 1 over n to the power of p. And what about these Trotter formulas? Maybe we get this better scaling back if we go to some higher order Trotter. And so first of all, what I want to say is the current bounds that exist in the literature for these higher order Trotter formulas also diverge if we look at the infinite dimensional case, because they again look at the operator norm. So we again have to go to some state-dependent analysis and look at the state-dependent Trotter error. And for example, in the case of second order Trotter, the bound that we provide in our paper looks like this. So we also provide bounds for arbitrary higher order product formulas. It's not restricted to second order, but the second order bound is obviously the simplest one, and you can already see what's happening for higher order product formulas here already. And what you can see is that you get like h1 cubed on phi, h2, h1, like a mixed term, and h2 cubed on phi. So the conditions, the domain conditions, that are even stronger than in the first order case. So the states that do not even satisfy the domain conditions for the 1 over n Trotter error scaling in the first order case will also not satisfy the domain conditions for higher order Trotter, and we will also expect higher order Trotter to converge slower. And this is actually what we find as well. We find analytic bound for the hydrogen ground state, for example, that scale in the same way as the first order Trotter, so you don't get any advantage from second order Trotter. And we also find alignment with numerical simulations in this scenario. And again, the scaling only depends on the orbital angular momentum quantum number in this case. And we also give bounds for like fourth order Trotter explicitly, and we also find numerically that fourth order Trotter also gives you a slower scaling and the same scaling as first order Trotter. So that means the entire higher order Trotter hierarchy breaks down for these states, which is quite remarkable, I think. So that is actually also the explanation for the title, Breaking Badly, because the Trotter hierarchy breaks down. And so practically this means that if we want to do simulation for these particular states, which have slower Trotter convergence, we don't want to go to higher order product formulas. We want to keep using first or second order Trotter, because if we compare the total number of unitaries to the Trotter error that we find, this is some numerical simulation, these are not our bounds, then we actually find that the first and second order Trotter errors are smaller compared to the number of unitaries that we have to implement. So the takeaway message is, for these states, use first or second order Trotter, not higher order Trotter. Okay, and now I want to summarize what are actually the contributions, what have we done here. So first, we provide general state-dependent Trotter error bounds for first and higher order Trotter. And so this enables that the study of the analytic study of Trotter error for the full unbounded systems that are considered in quantum chemistry. So second, one thing that we found by providing these bounds is that for states which have a low energy, like s orbitals, the Trotter error scales slower than what you would usually expect. So this actually practically would imply that the time scales until we will be able to do useful quantum chemistry simulations, like up to chemical accuracy, is slightly longer than what is currently claimed. And lastly, the higher order Trotter hierarchy breaks down for these states, so we don't get any advantage in scaling for higher order product formulas for these states. And so that means that first order or second order, they're pretty similar, is the most favorable way to do Trotterization in this scenario where we have these states which have slower scaling. There's some open questions as well that arise from this research. So the first question is, what about more complicated atoms and molecules? Because quite frankly, the hydrogen atom is very well understood, and we don't even need Trotter in order to implement that. And so there's some studies here that might actually give some ideas how to tackle this problem. But I would personally assume that that we don't get the problem of slower scaling for ground state of molecules, because if you think about it, if you have a molecule consisting of two atoms, then the ground state will probably have a high electron density between the two atoms, so it's not close to the 1/r singularity. So my suspicion is that we don't have this problem so much in molecules, which would probably be interesting in itself. Then also, what I mentioned already is, what about other quantum simulation methods? So what about qubitization, linear combinations of unitaries? Do we get can we see this effect of unbounded Hamiltonians there as well? And lastly, there has been this paper this year in Nature Communications, which kind of puts into question, is there even exponential advantage in quantum chemistry simulation compared to classical chemistry simulation? And the answer is kind of, maybe not. It's not been proved really yet. And so I think, or my hope is that because we do provide some analytical methods to bound the Trotter error of the full system, our methods might actually help to tackle this problem, even though the separation is not exponential and we just get a polynomially worse Trotter error. But the hope is that by looking at the full system without truncation, you get some insights into this. And with this, I would like to thank you, and I'm happy to take any questions.
Please, we have some time.
That nice talk. So I have a question and a comment. And the question is that, so I guess the point here is that the potential is unbounded, has Coulomb singularity. Otherwise, you have a smooth potential that's addressed in the literature, right?
Yes and no. I mean, the thing is that already if you have a kinetic energy plus potential energy, the Hamiltonian will be always unbounded.
Yeah.
Actually, the kinetic energy is even more singular than the potential energy.
That's right. But addressing the kinetic energy singularity, that has been addressed in the literature.
In which way?
I just checked your paper. You cited the papers. But really the intrinsic thing is the Coulomb singularity, which makes it in the potential, which makes it really hard.
I'm actually not sure if this is really the case. If really the Coulomb potential.
Okay,
is the
yeah.
problem. So I think the inherent problem of the inherent problem is that we have these unbounded Hamiltonians,
Right.
and the thing is that if you have unbounded Hamiltonians, then you will always find states for which Trotter converges slower, and you can prove that as well. This has been proved in 2018 by Ikinose. So also in the case, you will always find for Schrödinger operators, you will always find states where Trotter converges slower than 1/n.
Yeah. Okay. So my question is actually that you tested this for the ground state, but that's like one. Is that like a one particular function, or is it like a class of functions? Because you're talking about dynamics, is it right? It's not a function.
Yes. So this scaling holds for all s orbitals. For all s orbitals of.
But during the dynamics, it may not look like an s orbital. Does that make sense? I mean, you don't want to apply Hamiltonian to already the ground state, then it doesn't move. It's really applying to something else
that's
that
right.
has Coulomb singularity.
Now I understand. Now I understand.
Right? Yeah.
Yes, but the hydrogen eigenfunctions are a basis of your Hilbert space, so you can express every state that you want to look at in that basis. And if the hydrogen ground state appears in the linear combination of this basis expansion, you will get the slower scaling because this term is the slowest scaling one, so it will dominate the scaling. So you can do you can do superpositions of eigenstates. Of course, the hydrogen atom is a Hamiltonian, so its eigenfunctions form a basis of the Hilbert space. And yes. So
okay. Yeah. The comment is that we actually have a version of the algorithm. So very simple. It's like a first order Magnus expansion, and implemented in the right way, we can show that even the operator norm, you can address the unbounded operator. Maybe we can talk about that.
Okay, let's do it. I'm very interested in that actually.
We still have time if anyone else would like to ask.
Yes. So the way we do the numerical simulations is basically we put the molecule on a grid. Basically, we do a grid in position space, and then we do some spherical Bessel transformation because this is spherical symmetric, and by this you can diagonalize the kinetic energy, and then you just work in the diagonal bases, and where you can easily compute the matrix exponential. And for the potential part as well, the potential part just multiplies any wave function with -1/r. So if you do a grid in position space, so you basically do some position cutoff, you put some radial cutoff, and then you put a grid in position space, and then you just multiply any wave function by -1/r. Yes, that's right. No. Yes, I mean we were more interested in like, can we actually do this result holds for like the general bounds hold for all unbounded operators which have eigenstates. So this was the original motivation, and we were looking at like what kind of examples could we apply this to, and for hydrogen we can compute everything analytically. I'm not sure if you can still do this if you regularize. You can still compute things analytically. So.
Any last questions? Okay, if not, let's thank Alex and all our speakers in the session.